Hi, folks. In the first lesson, we saw the different ways in which three planes can interact. All right, so here what we want to do is we want to solve the system of equations, which means determine the x, y, and z values that satisfy all three equations. And then we want a geometric interpretation, because when you look at these three equations, they could geometrically represent planes. Okay, so we saw that there could be one point of intersection, no points of intersection, and different ways of having infinitely many points of intersection. So the first thing you want to look at when you're solving one of these questions is, are there any parallel planes? Okay, because that can really make the question certainly much simpler and sometimes much quicker if you can tell that there's two planes that are parallel and distinct. And here what I notice is that equation 1 and equation 3, well, 3, 4, 1, 6, 8, 2, they're parallel planes. So we see that the normal vector in plane 3 is 2 times the normal vector in plane 1. But not just that, the d values also differ by a factor of 1. So that means plane 3 and 1 are coincident. Okay, 1 and 3 are coincident. So essentially that means that these two represent the same plane. And now I'm intersecting it with plane 2, which is not parallel. So what we have is we have the scenario where you've got two planes that are essentially the same, and then another plane which is, so here I'm looking at a cross section, another plane which is not parallel to the other two, so they intersect in a line. So this is just a cross section. You have to imagine that there's, a line coming out of the sheet that represents the intersection of these three planes. Okay, so essentially what I can do is forget this equation here because it's equivalent to equation 1, and now I'm essentially solving this as the intersection of two planes. All right, so let's just go through it. It's a good review of remembering how we solve the intersection of two planes. So let's start by, and let's say I eliminate the z's. Okay, so what I'm going to do is I'm going to take 2 times equation 1, okay, and I meant 3 times equation 1, because this is 3z. So if I do 3 times equation 1, and then I'm going to subtract equation 2. All right. Now, if you need to write this out, not a bad idea to do it. We have a certain amount of experience now, so we'll see if we can do it without writing it out. So 3 times 1. So 3 times 3 is 9, minus 5 is 4, so we have 4x. And then here, 3 times 4 is 12, minus 2 is 10, so plus 10y. And then here we have 3z minus 3z is 0, which is what we want. And now we have 3 times 4 is 12, minus 2 is 10. All right. And so what we expected to get was a relationship between the two of the variables, in this case here, x and y. And so now I'm just going to solve one in terms of the other. Okay, so since I have the 10 here, I think what I'll do is I'll solve for y. So we have 10y is equal to negative 4x plus 10. So y is equal to negative, so 4 over 10 is 2 over 5, so 2 over 5x plus 1. All right, now that I have y written in terms of x, my goal is to write z in terms of x. So this is where now, since I've got the lone z, I guess I'll use equation 1. I'm now going to input my expression for y into equation 1. So we have 3x plus 4y. So here I'm going to replace y by negative 2 over 5x plus 1 plus z is equal to 4. And now I can solve for z. Okay, so let's do a little cleaning up here. So here we have 3x, and this is going to be minus 8 over 5x, and this is going to be plus 4. And then here plus z equals 4. So here, hey, look at that, subtract 4 from both sides, get that out of the way. And so here, what do I have? I have z is equal to, and we'll bring this to the other side, and what do we have? We have 8 over 5x minus 3x, and 3x, in fact, instead of writing it as 3, let's write it as 15 over 5. Okay, so in the end, what do we have? We have z is equal to 8 minus 15 is negative 7 over 5x. Okay, so remember how this works is we've written y in terms of x, now we've written z in terms of x, and so now we're going to let x be our parameter. X is going to represent our parameter t. Okay, and so now our equation, okay, so we're going to have infinitely many solutions. X is going to be equal to t. Y can be written as negative 2 over 5 t plus 1. And then z can be written as negative 7 over 5 t. And here, t can take on any real number. Okay, so this represents all the possible solutions. As expected, we have infinitely many solutions. And now for the geometric interpretation, what does this represent? That the planes intersect in a line. Okay, so here, because of this special scenario, the algebra portion of it was just doing something we already knew how to do. All right, so let's move on to another example. And the first thing I'm going to notice about this example, okay, if you take a look, is none of these planes are parallel to each other. All right, so that means there's three possible scenarios that we can have when we've got three planes that are not parallel. Okay, so let's see what happens. So we're going to need something a little different because now we're dealing with three equations and three unknowns. So first of all, let's try to recycle something we already know how to do. So we know that when we're solving systems of equations, we can use elimination or substitution. Now, I'd say substitution is not an unreasonable thing to try because x is easy to isolate. Here, the y's, these z's are all easy to isolate. But I want to try to stay away from substitution as my main way of solving these systems because, you know, what if I don't have any nice, easy variables to isolate? That means I'm dealing with fractions right off the bat. So as I usually try to encourage people to do, is we're going to work with elimination. Okay? Let's see if we can recycle elimination to make it work here. Okay? And this is going to be our strategy. Our strategy is to start by eliminating a variable. Okay? But I'm not going to eliminate it once because say I eliminate, I'll eliminate z here. Okay? You know, y would have also been another nice, in fact, they're pretty all easy to work with, but let's say I start by eliminating z. If I eliminate z using the first two equations, I'm going to end up with an equation with an x and a y. Well, guess what I'm going to do? I'm going to eliminate z in another pair of equations, and that's just going to give me a second equation in x and y. And all of a sudden, I'm going to take this three equations and three unknowns, and I'm going to produce two equations in two unknowns. All right, so let's go ahead and do that. So the first thing I'm going to do is I'm going to eliminate the z's using equation 1 and 2. So I'm just going to have to subtract the equations. All right, so I'm going to do equation 1 minus equation 2, and let's see what happens. Okay, so x minus 2x is negative x. By the way, if you feel that you should be writing this down, perfectly fine, but you know, see if you can get comfortable doing it this way. Okay, 2 minus negative 1, so 2 plus 1 is 3, so plus 3y. Z minus z, 0, exactly what I expected, and 12 minus 5 is 7. Okay, so I'm going to call this equation 4. I have an equation now in only x and y. So remember what we said our goal was. Our goal is to now do the same thing with another pair of equations. I'm going to eliminate the same variable. I'm going to eliminate z. Now, I could use 2 and 3. That would be easy. I could use 1 and 3. That would also be easy. Okay, so let me use 1 and 3. Okay. Certainly, I could have done 2 and 3, would have been just as easy. Okay, but here I'm going to have to multiply this by 2 and then add the equations. So I'm going to do 2 times equation 1, and then I'm going to add equation 3. Okay, so that's going to be 2x plus 3 is 5x. Okay, This is going to be 4y plus y is 5y. Okay. Here I have 2z plus negative 2z. So 2z minus 2z is 0, exactly as I wanted. And then here I have 2 times 12, 24, plus 1 is 25. And look what we've done. We've now created two equations in the same two unknowns. And guess what I know how to do? I know how to solve two equations in two unknowns. So what we can do is solve for x and y here. Now, if you take a look at this equation, remember, think about what the legal operations are on equations. I can multiply the same thing to both sides. I can add and subtract equations from each other, okay? Or I can divide both sides of an equation by a number. So I'm actually going to not work with 5x plus 5y equals 25. I'm going to work with an equivalent equation. I'm going to divide both sides by 5. So x plus y equals 5. That makes my life a lot easier. So I'm going to call this now equation 5. And now I'm going to work with these two equations to solve for x and y. And it's actually set up pretty nicely because look what I have. Negative x, positive x. I could just add equations 4 and 5. And what do we get? Negative x plus x, 0. 3y plus y, 4y. And here, 7 plus 5 is 12. And lo and behold, look what I just did. I just solved for the y value for, presumably, the point of intersection of these three planes. But let's see where the rest takes us. Because now that I've found y, I can now go back, as I normally would, and use this equation to find x. Or in fact, that equation to find x doesn't matter. So here, let me just continue up here. So this seems to be the easier one. So I'll take equation 5, and wherever I see a y, I'll replace it by 3. Okay, x plus 3 is equal to 5. So x is equal to 5 minus 3 is 2. And there we go. We found our x value. But now that we know what x and y are equal to, I can now go back to one of those equations that has all three and solve for z. Okay, so say I take equation 1 now, and wherever I see an x, I replace it by 2. Wherever I see a y, I replace it by 3. And look at that. I can now solve for z. So 2 plus 6 is 8. So z is equal to 12 minus 8. Z is equal to 4. And there you go. So there's only one triple that solves all three equations. X equals 2, y equals 3, z equals 4. And the geometric interpretation is that the planes intersect at the point 2, 3, 4. Okay, and just as you would have done back with two equations and two unknowns, if you want to check your answer, well, let's just take these numbers and stick them into our equations. So 2 plus 2 times 3 is 6. So 2 plus 6 is 8, plus 4 is 12. There you go, that works. 2 times 2 is 4, minus 3 is 1, plus 4 is 5. That works. 3 times 2 is 6, plus 3 is 9, minus 2 times 4 is 8. 9 minus 8 is equal to 1. So this point here exists on all three planes. Okay, so just to recap the strategy here is to first start by eliminating one of the variables using two equations. Then you're going to use another pair of equations to eliminate the same variable and then solve the resulting system of two equations and two unknowns. And once you do that, you can just work backwards to find all 3 points. All right? So do one more example here. Now, at this point, you might want to actually stop the video and give it a try yourself if you'd like to do that. Okay, so if you want to do that now. Okay, so I'm going to solve this now here. So first thing I look is very quickly take a look at the 3 equations, and I see that none of them are parallel. All right, so here I've got a few choices that I can use, but I think what I'm going to do is I'm going to work with x in both instances. So I'm going to use the first two equations to eliminate x, and then I'll work with equation 1 and 3 to eliminate x again, okay? Because I've got this nice x, makes it easy. I could have done something similar with the z's, okay? Really doesn't matter. So let's start here. So I'm first going to multiply equation 1 by 2, okay? And then I'm going to subtract equation 2. So 2x minus 2x is 0, okay? Negative 6y minus negative 5. So negative 6y plus 5 is negative y, all right? And then here, what do we have? Negative 4 minus 1, negative 5. So negative 5z, all right? And then here we've got negative 18 minus 3, negative 21, okay? So that works out nicely. Let's now use equations 1 and 3 to, again, you'll always remember that it's important that you're eliminating the same variable. So here I'm going to do 3 times equation 1, except now I'm going to add equation 3. Okay, so 3x minus 3x, 0. Okay, negative 9 plus 6 is negative 3. Okay, negative 6 plus 2 is negative 4. And then here we have negative 27 plus 8 is negative 19. Okay? And so, as before, I have now a system of equations involving only y and z this time. Okay? So I'll call this equation 4, and I call this equation 5. So let me now start by solving this system. So I guess I'll multiply equation 4 by 3. So 3 times equation 4. So what do we have? We have negative 3y minus 15z, and then equals negative 63. Okay, and now I'm going to have to subtract them. So negative 3y plus 3y, very good, gets eliminated. Here we have negative 4 plus 15. So negative 4 plus 15 is going to give me 11z. And then here we have negative 19 plus 63. I think that one there, I'm going to be careful and use my calculator. So negative 19 plus 63 gives me 44. Oh, and that's a really nice number here. Okay, so now I can solve for the z value. 44 of 11 is just 4. And there you go. I just solved my first variable. So again, what did I do? I eliminated x using equations 1 and 2, then eliminated x using equation 1 and 3, and solved the resulting equation. Okay, so I'm going to use now equation 4 to solve for y. So negative y, oops, not equals. I'll just put it in exactly as written. So negative y minus 5 times z, which now we know is equal to 4, is equal to negative 21. So I'll bring the y to the other side. Y is equal to negative 20 plus 21. And hey, look at that. That turns out to be really nice. Okay. So let's now take this y and z and input it into one of these equations. Looks like number 1's the easiest one to use. Okay, so x minus 3 times y minus 2 times z equals negative 9. So what do we have? We have negative 3 minus 8 is minus 11. And bring the negative 11 to the other side. Negative 9 plus 11 is equal to 2. And there we go. Turns out that this system of equations, again, has a unique solution. So geometrically, because remember it also asks for the geometric interpretation, we say that the planes intersect at the point, okay, 2, 1, 4. All right. So just a recap here. Okay, always check to see whether there's parallel planes, because that could definitely make your life a lot easier. You know, so for example, here, had this been 9 instead of 8, right off the bat, you could have said, oh, 2 planes are parallel and distinct. No solutions, you're done. Okay. In the case where there aren't any parallel planes, you're going to follow this system of eliminating a variable once, using another pair of equations to eliminate a variable twice, and then solve the resulting system in 2 equations and 2 unknowns. And then you go backwards to determine the other points. Now, what we're going to see in the last video today is that sometimes when you have 3 planes where none of them are parallel, you don't always have one single point of intersection. So we're going to take a look and see what those look like when you're solving that scenario. Okay, that's it for now.